Hi.
How's it going, Jackson?
Not actually decently well after
Pretty good.
well,
That's good.
yesterday. Yeah.
That's better than not good. So hello, everyone. Today we are beginning our new unit. To get started, what I want you to do is I want you to answer the warm up in the Zoom chat here with whatever your best guess is. The question I'm sort of asking you is if an astronaut were to throw a football in space, what would happen to the football? Would it ever stop or change direction? So take a couple of minutes to try to think about this, and then let's see if we can get a poll. I don't want a poll, but like a few answers here of what you think would happen. Um, you may have a better understanding of this if you've watched a lot of space movies, but if you haven't, that's okay too. So let's take maybe 2 or 3 minutes to try to think about this and what would happen to the football. I don't expect you to know what would actually happen. but I am curious to see what you might think. So, if an astronaut were to throw a football in space, what would happen to the football? Would it ever stop or change direction? For today, there is a graphic organizer that I would recommend filling out. It is on Canvas. It is called Forces in Motion Graphic Organizer. You should fill this out as we're going through these slides here and then submit it on Canvas whenever you are done. I think I had the due date set for today at like 11 a.m. So you should be able to finish it by then. So open that up on Canvas and fill this out as we're going along. But let's take another minute or two. If an astronaut were to throw a football in space, what would happen to the football? And whenever you're ready, you can put your opinions in the Zoom chat here. Ooh, Galen. First, it has to be assumed that the astronaut is on a solid surface to be able to throw the ball. The ball would then maintain a constant speed until it is impacted by a separate force, such as a gravitational field. The ball will slow down on Earth because of frictional resistance and gravity. That is very interesting, Galen. Very, very, very interesting. You, of course, do not have to have as verbose of an answer as Galen. I'm looking for opinions here. Let's take another minute or so before we move on here. Ooh, Sam has an answer. It wouldn't stop or change direction unless it began to orbit something. It would just keep moving the direction it was thrown. The ball would never stop or change its direction. Wow, we have a lot of interesting ideas here. You could be right. You could be wrong. I won't tell you what's going to happen until later on. But I think we have a general idea of what's going to go on here. We'll take another 30 seconds or so before we start moving on. Meanwhile, if you finished, you should open up your graphic organizer on Canvas. Start filling that out and we'll submit it afterwards. Okay, so as for an agenda, we're finished. We just did the warm up. In terms of slides, there's a graphic organizer on Canvas that you should fill out and submit it. We will finish it today, so I don't know, but we will finish it today. And then for asynchronous participation, fill out weekly server mechanics before we end at 6 p.m. This will apply more for next week, not so much for this week. But for today, we're going to fill out the graphic organizer, and we will actually do a FET afterwards after we finish this. But for now, just open the graphic organizer. Mateo says it goes in direction unless it hits something about comps form gravity. Interesting, interesting. Ooh, interesting. Considering the spin and spiral of the ball, it may change direction more noticeably. Interesting. Gabe says it will continue to accelerate forever unless something goes away because of inertia. Chloe says there's less gravity in space and the ball will probably move in a certain direction unless hindered by another object. Wow, I think we actually, now I feel like there's not much point for me teaching this because I feel like you already have a good grasp of it. But don't worry, we'll actually talk a little bit more about this today. So here is probably the main conceptual understanding, idea that most of you are somewhat familiar with, or at least hinting at right now. So this is the first thing we want to know, and that is, this is very important. So we're talking about Newton's first law of motion here. An object at rest tends to stay at rest, and an object in motion tends to stay in motion with the same direction and speed. Basically, I think the best way to think about this is objects are lazy. Whatever they're doing, they want to stay doing. So if you think about it, if you let's think about it like practically, right? If you are sitting on a couch, right, you're gonna want to stay on a couch. because you don't want to do anything. And if you're driving, right, you want to stay driving. You don't want to be, you don't want to, you don't really want to, it's very natural just to stay at the same speed. So this is sort of the same idea here. An object tends to stay at rest. So in an object that is not moving, right, they want to stay not moving. And an object that is moving wants to stay moving, and they don't want to change directions and they don't want to change speed. So this concept in general is called inertia, which is something that I believe some of you have already heard of. But inertia is literally this first law. Inertia just basically means that an object doesn't want to change what it's doing. If it's moving, it wants to stay moving. If it's at rest, it wants to stay at rest. So this is very important when we talk about acceleration and stuff. This we talk basically like this is like the reason why this is important is because when we look at different problems, right, we'll look at objects' motion, right? We'll look at an object moving, and then we'll want to look at are there any forces applied on it, or is there an acceleration? And the thing that you want to remember is that if it's moving, it wants to stay moving in that direction and speed, and if it's at rest, it wants to stay at rest. So that's the first law of motion. I think I'm sure you've seen something like this before. I am going to, I just like how Wikipedia is a really good place to learn. Urban Dictionary is also a really good place to learn physics. On Urban Dictionary here, inertia is the reason why you have to use some sort of effort to move something. And this is just basically saying that an object at rest wants to stay at rest, and a body in motion will want to keep moving at a constant velocity. And this is why in the previous problem, when we thought about the astronaut, the football in space, because space, there is no friction, there is no air resistance. A football, when you throw it in space, it's not going to move. It's not going to stop moving. It's not going to deviate. It's not going to speed up unless a force acts on it, which is gravity. So this is just the basic concept of inertia. And I think you may have seen this before, but if you haven't, this is what inertia is. What determines an object's inertia is its mass. So basically, the bigger an object is, the harder it is to change what it's doing, right? So it's very easy to, like, if you had a toy car versus a real car, right? It's really easy to stop the toy car. It's really easy to start the toy car, right? And that's because it's much smaller. If you've ever tried to push your car before, you would know that that's not very easy. And that's because that bigger car has more mass and it has more inertia. And if something has a lot more inertia, it means that it's harder to get moving, right? It's harder to start, and that it's also harder to change its motion, right? A semi truck that's moving is pretty hard to stop, but a semi truck that has stopped is pretty hard to get moving. So an object's inertia is determined by its mass alone, and that is very important. So what I want you to do in your graphic organizer, we're gonna watch a quick video here about some pennies on a card, and I want you to write down why you think the pennies don't fall over. So we'll take a minute or two for you to think about this and write it down. You probably have seen something like this before. You know the magic trick where you have like the tablecloth and then you have all the plates on it and then you pull the cloth out. It's the same concept here. So just think about it for a minute, take a minute to write it down, and then we'll move on here. Okay, so hopefully that was enough time to think about why the pennies don't fall over. And we will talk a little bit. So how I would think about this is the pennies are initially at rest. They're stationary. They're sort of stacked upon each other. They're stationary and they don't want to move. So when you flick the card through the pennies, because the penny's at rest, they don't want to stay moving. And so the force that is applied by the card, it's not really able to overcome the inertia of the pennies. And so the pennies don't move. And that's how I would think about it. It's the inertia of the pennies that prevents the pennies from falling over.
The pennies are also heavier, right?
Yep. So relative to the card, the pennies are a lot heavier, and especially there's quite a few pennies. And so because the pennies are relatively a lot higher than heavier, more massive, sorry, than the card, the amount of force applied on the card is not a lot. And so you have a small force with a large mass, which means that the pennies won't really do anything. And we'll talk a little bit in a second about what the implications are in terms of mass. Okay, so in order to change the direction of the football, so we first talked about what would the football do in space, and we sort of agreed, at least it seems like we've agreed that the football is not really going to do anything. It's just going to stay in the same. It's just going to keep moving unless something else occurred. So what I want us to think about is what would be required to make the football speed up, slow down, or change direction. We already have a few answers here. What I'm going to do is what I'm just going to do is I'm going to sort of sum up what people have sort of thought about. I think most people, quite a few people have said that in order to change the motion of the football, you need to apply something called a force. So the force is something that you have to apply in order to change the motion of an object. If you don't apply a force, the object's motion will always stay the same. So this is where we introduce Newton's. The astronaut would also move in the opposite direction of the football. We will actually talk about that in a second, but for now, we're just focusing on the football. So what we're going to do is we're going to talk a little bit about Newton's second law of motion. Newton's second law of motion, as suggested by Urban Dictionary, is that basically what the acceleration of an object. So how an object's acceleration is basically an object's change in its motion, right? Velocity is an object's motion. Acceleration is the change in that motion. And the amount of acceleration, the amount of how much the motion changes, depends upon how much force you're applying, the net force you're applying, and how much mass the object is. So in other words, an object's acceleration, right, it depends on how the net force acting upon it and its mass. So in order to change an object's motion, in order to accelerate an object, you need to apply a force. And how much the object accelerates depends upon the net force on the object and the mass of the object. So TLDR, acceleration depends on net force and mass. So acceleration depends on net force and mass. So here's another way of thinking about Newton's second law is an object will accelerate if acted upon and unbalanced or net force. So what a net force means is that the forces are imbalanced. So forces have directions, and you can think of it as some forces are acting in some directions, other forces are acting in other directions. And if the forces cancel out, there is no net force. However, if the forces don't cancel out, there is an unbalanced force, there is a net force, and that net force will cause the object to accelerate. How much the object accelerates is directly proportional to how much force you apply. So if you apply more force, you're going to get more acceleration. If you apply less force, you're going to get less acceleration. Similarly, well, inversely, actually, how much an object accelerates is inversely proportional to the mass. So if you apply force to a more massive object, it's going to have less acceleration. If you apply the same amount of force to a lighter object and a less massive object, it is going to have more acceleration. So if you apply more force, you're going to get more acceleration. Less force is less acceleration. More mass is less acceleration. Less mass is more acceleration. Yeah. And an object will accelerate if there is an unbalanced or a net force. This is very important. If there is no net force, if the forces cancel out, and we will talk a little bit what it means to cancel out. But if the forces cancel out, there is no acceleration. If you look around your table or bed or wherever you are right now, objects that are not moving right now or not accelerating, it's not because there's no forces acting upon it. It's just because the forces are all canceling out. And even if an object is moving, right, it doesn't necessarily mean there's a net force. A net force only means that the object is accelerating. The more force you apply, in other words, the harder you push something, it'll cause more acceleration. And the heavier an object is, it's going to accelerate less. And the equation we use to describe this is very important. Very, 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 very important. Very important. I can't even iterate how important this is. This equation is F equals ma. You may have heard about this before, but if you haven't, welcome to the world of physics. This is probably, I think, one secret I have in terms of doing well on AP tests is if you don't know what to do, just write F equals ma and you'll get partial credit. I actually think that's kind of, I actually think that does kind of work. But in general, F is equal ma is probably one of the most important equations in physics. What it means is the amount of force you apply is equal to the amount of the mass it has times the amount of acceleration. And then you'll see how and because force is directly proportional to acceleration, more force is more acceleration, and mass is inversely proportional to acceleration. This equation is extremely important. If you forget this equation, I will never let you hear the end of it. So you need to know this equation. And because it's only 3 letters, I expect you to remember it on your dying bed. On your gravestone, I expect you to write F equals ma. If you don't, you will hear from me from my gravestone. So F equals ma, remember it. If you don't remember it, I'll never let you hear the end of it. Yeah, very important. Also, MA is MA, so if you don't know MA, that's, you don't know, like MA is like where we are, and then like, MA is mass. Yeah, so you know it. Yeah. Okay, so this is, I said TLDR because I sort of meant this as like a too long didn't read. Actually, no, right, as you can tell from here, it is kind of long too. But this is sort of how I would sum it up as well. So in object's motion, stationary or moving, that does not change ever, unless there is a net force on it, which means that an object will not accelerate or decelerate unless there's a net force on it. So an object that is driving, right? So an object that is moving does not necessarily mean it has a net force on it. There's only a net force if its speed or direction is changing. So if it's moving or if it's stationary, it does not change its motion unless there is a net force on it. So what is a force? I don't think we talked a little bit about force. I said we need to apply force. What is a force? Well, a force is literally just it's just a push or a pull, right? If I push something, if I pull something, I'm going to change its motion. So that's it. That's what a force is. It's a push or a pull. A lot of different objects there are a lot of different types of forces. A lot of different things can essentially push or pull your object, or slow down, or speed it up. So, but it's basically literally just you can think of it just as a push or a pull. And one thing that you should consider is just because an object is moving doesn't mean it is under the influence of a force. I said this like 5 or 10 times, but this is extremely important. Just because an object is moving doesn't mean it's under the influence of a net force. It could mean that it's under an influence of a net force, but it doesn't mean that it necessarily is. Another thing you should think about is forces can act in multiple directions. The reason why this is important is because if forces are acting in the same direction, they can sort of add together, sort of like vectors. Forces are vectors. So if forces are acting in the same direction, they can sort of add together. And if forces are acting in opposite directions, they can sort of counteract each other. They can sort of subtract from each other if they are from acting in opposite directions. A net force means that after you add and cancel and subtract and counteract all the forces, there is an overall non-zero force acting on the object in some direction. So this water bottle that is stationary on the table, there is no net force on it because it is not accelerating. But when I throw it at you because you are on your phone, there is a net force on it when there is a net force on it from the motion from when I'm holding it. After I throw it, there's no net force. We'll see what that means in a second. So we're going to look at here is what the force is on a football after you throw it. This is on Earth, so this is not on Earth. This is not in space. So let's look at all the forces on football. So one thing that is extremely important to consider is after it leaves your hands. And this is where this is an extremely important point. I'll talk about it in a second. So on this football here, we know there's one force acting on it. This is the force called gravity, right? Gravity always pulls objects downwards to the center of Earth. So this football is being pulled downwards due to gravity. And that's why objects, right, in the air, they fall down, right? So this football is falling down because of the force of gravity. There is also another force called air resistance. Air resistance is basically a force that pushes against the object. It tries to slow it down. And this is why an object will always stop eventually. And that's because of the force of air resistance. Air resistance does slow down objects that are moving. If you note here, there is one force you may consider, okay, but what if the ball is moving forward? So isn't there a force there, right? I throw the ball, isn't there a force there? Well, the thing is, after you release the ball, there is no force actively pushing on the football. It's in the air, it's moving, but there's nothing that is actually pushing it forwards anymore. This is very, very important. It's very natural to think, okay, I threw the ball, there must be some sort of applied force on the ball. But after you throw it, after it leaves your hand, there's nothing actually pushing it forwards anymore. There's no rocket engine. There's nothing pushing on a ball. It's just moving forward. It's moving forwards, but there is no forward force on it. There is a force pushing against it, an air resistance, and there's a force pushing down on it, but there is no net force acting on it. There's no, forward force acting on it. So if you notice here, I have one vector arrow going down called gravity. I have one vector arrow to the right called air resistance. Which means that the net force acting on the ball is this red line. It's some of the arrows here. It's a net force. It's a vector that it's pushing the ball downwards and to the right. So the key thing here is that the forces will add up together because they're all vectors. And then if you want to find the net force, you just add up the vectors. And you'll have the net force. If you aren't sure what a vector is, think about it. It's basically just what direction the force is and how strong that force is. So If you have a strong force, you're going to have a big vector arrow. If you have a small force, you're going to have a small vector arrow. And the direction of the arrow tells you is the direction of the vector, which tells you the direction of the forces. In this case, the gravity has the vector gravity is pointing downwards because it's pulling the football downwards. And then the air resistance vector is pointing to the right because it's moving against the motion of the ball, so it's slowing the object down. So this is where we talk about what happens to the astronaut after they throw the ball. So I think Jackson already answered this. So what happens to the astronaut is after the astronaut throws the ball, after she throws the ball moves forward. The astronaut actually moves backwards. Yes, the astronaut actually moves backwards. Mateo, absolutely correct. The astronaut will move backwards after she throws the ball. Why does that happen? Why does that happen? Because of something that we call Newton's third law. So Newton's third law says for every action, there is an equal and opposite reaction, which means that if you do something, that thing will do the exact same thing back to you. So if I apply a force on a ball that I throw at you during dodgeball or because I don't like you, the ball is throwing me backwards too, as well. When you apply force on an object, that object is also applying a force onto you. For every opposite action, there is an equal and opposite reaction. This is very important. This is something that's harder to visualize on Earth. Because when you throw a football or when you throw a ball or when you push an object on Earth, you don't really move backwards, so you can't really see that the opposite force being applied to you. And that's because usually we have other forces acting upon us. We have the force of friction, air resistance. Oh yes, wow. Yes, we've the best example. One of the best examples here. So we'll talk about this. So how can you demonstrate Newton's third law? So write down a very basic experiment you can do in class or at home that would demonstrate Newton's third law of motion. So you don't actually have to write this down. If you can think of one, that would be great. The best example that, one good example that some people have mentioned just now is gun recoil. You should not do this experiment at home or in class. I would actually recommend you never do this unless it's in a video game. So one thing that is something that you should consider that happens with any sort of firearm or any sort of honestly, any sort of projectile, like rockets are pretty good at this too. In order to push something forward, that thing will end up pushing something back. Is bouncing a ball another apt comparison? Is bouncing a ball another apt comparison? So oh yes. It actually is a very apt comparison. Yes, yes. So when you bounce a ball, when it hits the ground, the ball is putting a force on the ground, and the ground is also putting a force back onto the ball, which is why the ball comes back up, right? So the ball comes back up because the ground is exerting a force on the ball and it's coming back up. Guns are good at this because when you shoot the projectile or the bullet forward, the gun will also push you back, which is actually very dangerous because it can do a lot of damage to you. Bows are also good at this. Rockets are good at this. Another good example is kicking an object is stationary. So kicking a stationary ball can hurt your foot. If you ever try kicking a medicine ball or a dumbbell or something, it hurts because when you kick the dumbbell or something, that object also applies a force back to your foot, which can actually hurt. What are some other good examples of demonstrating the opposite equal and opposite reaction? Actually, rockets in space are actually a really good example of this. The way rockets work in space is you're basically ejecting a bunch of gas backwards. And in the process of ejecting the gas backwards, right, that gas is exerting a force forwards, and that pushes your rocket forwards. So that's actually a good example of how rockets work. Whenever you wear a car, you have to wear a seatbelt or you're launched forward. Let me think of how that works. So that might be a better example of Newton's first law. I think so when you crash a car, your inertia is actually what keeps you moving forward. So when you crash your car, right, you are physically moving. So you want to stay moving. So even though the car has a force applied to it, the car is stopping, you are still moving forward. And this is why you should wear a seatbelt, because the seatbelt will pull you back. Now, I don't know if the seatbelt is the best example of the reaction force, because I'm not really trying because the way I can think about it is when you crash a car, the seatbelt is applying a force onto you, and you are applying a force back onto the seatbelt. I guess that's when you can think about it. So that is true in a sense. It's kind of hard for me to visualize. I think it's a better example of Newton's first law, where if you're moving, you want to stay moving. If you hit a baseball with the baseball bat, yes, this is also a really good example here. So if you watch baseball, when you have a baseball bat and then you hit a ball, a lot of times you'll see, especially with wooden bats, that bat will break. And that's because you're hitting the ball forward, but the baseball will also exert a force backwards onto the bat, and that can potentially break a baseball bat. So that's also a good example of Newton's third law. If you can think of another good example, feel free to hit me with them. I feel like you guys are just doing my job for me, but hey, it says you have to write down the class experiment, not me. So I don't have to tell you. If you hold something heavy still in the air, you can feel the weight of the object. Yes, that is true. That is true. You are exerting a force on the object is exerting a force on you. That is 100% correct. Yep. So we have a lot of good experiments here. You guys are all very creative. So those are the three major laws of Newton's laws that you should know. Each one is very important. You don't necessarily need to know which law is which law. Like I'm not going to say what is Newton's first law because I mean I don't really know that in my head. But you should know all three. You should know what the concept of inertia is. You should know that F is equal to ma, and you should know that every action has an equal and opposite reaction. These two are extremely important. These are honestly a huge foundation of physics. If you forget one of them, it will have very drastic consequences for life. So don't forget them. So hopefully you're able to finish most of your graphic organizer. If you have, try to please submit it on Canvas. I'm not going to grade it, and I'm not going to grade the next thing we're going to do, but you should still submit it because you should do it. What we're going to do next is we're going to do a FET. You may have done a FET before. If you haven't, that's okay. A FET is basically like a little simulation. So on Canvas, I'm also going to put a link right now into the chat. What we're going to do here is we're going to do a FET. We're going to do a simulation. So in this FET here, it's going to be related to forces of motion. We will try to do as much. Oh, my voice is cracking all the time here. So we're gonna do the FET here. We're trying to finish as much as we can. I don't think we'll be able to finish all of it, but we should be able to do most of it. What you're gonna do here is you're gonna do a bunch of simulations. The point of this is to try to help you visualize what forces actually do. So you're gonna apply a bunch of forces on a bunch of boxes, and then you're gonna try to see what that does to the box. So you'll have here, you're going to apply a bunch of forces to a box in different directions. You're going to look at how the mass of an object affects the amount of force you apply to it. You're going to look at the acceleration, and then you're going to graph it a little bit. Hopefully it won't take you too long. If you can't finish in class, you should be able to finish it at home in a very reasonable amount of time. So we'll try to do as much as we can. If you have any questions, please let me know about anything, FET, life, force, you can let me know. But we'll try to finish as much of this as we can today. So, oh, okay. Okay, so we got a minute left in class, so I'm going to wrap up here. We are going to finish this for homework, but I don't think it should take too much time, hopefully. And you will find that if you are especially clever, you will be able to do a lot of these stuff without actually having to redo the time trials, essentially. So if you can figure out how to be clever, I always encourage you to do that. You do not have to follow the directions explicitly. If you can be clever, I encourage you to be clever. Try to finish everything by next Monday. It should not take you hopefully more than 20 minutes or so. Once you're able to do that, we will move on to our next part of this concept. But that is it for today. Other than that, I will see you next Monday.
Hey, thank you. Have a good day.
Thank you.
Thanks,
Thank
Mr.
you.
Hu.
Thank you, Mr.
you.
Hu.
Thank you.
Thank
Thank
you.
you.
Thank you, Mr. Hu.
Thank you. Bye-bye. Bye-bye. Farewell.